Hi class, welcome to the final lesson in Unit 9, Kinetics and Equilibrium. As you know, a test will come soon. Look for a review sheet on Google Classroom. You may also use guided notes as you follow along with this video. In this video, we are going to study Lechatellier's principle, which examines how equilibrium will shift when stress is applied to a system and how the amounts of products and reactants will change as a response to that stress. Let's go. So let's look at what Lechatellier's principle is. It says that a system at equilibrium will stay at equilibrium until an outside force or stress is added. Now, once an outside force or stress is added, the position of equilibrium will shift or change to alleviate that stress. So if you increase the temperature of a system, the system will try and decrease it. If you add reactants, the system will try to get rid of it. Whatever you do, the system will try to undo it to maintain a new equilibrium. So let's explore equilibrium so we can talk more about this shift. So here is a system at equilibrium, and we know that a stress will disrupt the equilibrium by speeding up either the forward or the reverse reaction. So in this reaction, we know we're at equilibrium because the concentrations are constant, as represented by these parallel lines. But the concentrations at the new equilibrium are different. Lechatellier's principle focuses on this circled region. What happens to the amounts of reactants and products in response to the stress, and how does equilibrium shift in order to be reestablished? So we are going to stress the system or disrupt the equilibrium by adding hydrogen. You can see that immediately after the hydrogen is changed, the system has responded. So now the lines are no longer parallel. But given a little bit of time, a new equilibrium will be formed. The lines will be parallel again. But you can see that the amount of hydrogen and nitrogen go down while the amount of ammonia goes up. Just a little bit more terminology before we look at some examples of how this shift or change occurs. So anything that increases the concentration of the products is said to shift right or favor the forward reaction, as the forward reaction ends on the right. And anything that increases the concentration of the reactants is said to shift left. We could also say that the reverse reaction is favored. That's because the reverse reaction ends on the left. We can use a seesaw to help us determine both the reactant and product change and the equilibrium shift, which we'll show you shortly. But what you should remember from your playground days is that if one side of a seesaw is up, the other side has to be down, or vice versa. There are three stresses that will shift equilibrium: a change in concentration, a change in temperature, or a change in pressure for gases, which can be accomplished by a change in volume. Let's look at change in concentration. When a substance is added or the concentration is increased, equilibrium will shift away from the side of the reaction in which it was added. And if a substance is taken away or the concentration is lowered, the equilibrium will shift towards the side of the reaction of the substance that was taken away. Let's look at some examples so we can better understand. Let's look at a hypothetical system where we have reactant A and B in equilibrium with products C and D. If we add more reactant A and B, you can see the system is stressed. More A and B will collide, and in order to reestablish equilibrium, we will decrease the amount of A and B and increase the amount of C and D. The particles moved toward the right, so equilibrium shifts right. So what happens if we increase products C and D? Again, you can see we're stressed. There'll be more collisions between the products. In order to reestablish equilibrium, we will move products from the right to the left so equilibrium shifts. And finally, what happens if we remove the products? Again, we're going to shift equilibrium. In order to replace the missing products, we're going to have to move some particles from the left to the right. So equilibrium will shift right. Let's look at an actual chemical reaction so we can see how we can apply the seesaw method to predict the change in concentration and the shift of equilibrium. Here we have a reaction for the synthesis of ammonia. It looks something like this, where these white particles are hydrogen, the blue are nitrogen, and these complexes are ammonia. When they are at equilibrium, their concentrations are constant. But you can see that this reaction is exothermic because heat is a product. Now, if the forward reaction is exothermic, then the reverse reaction will be endothermic. Now we want to see what will happen if we add a stress to the system, such as adding more hydrogen gas. Now I'm going to show you how you can equally determine the direction of the equilibrium shift and the changes in concentration due to a stress applied to a system at equilibrium. So the first thing you want to do is imagine equilibrium. When you imagine equilibrium, you're going to draw a seesaw which has a fulcrum directly under the double-headed arrows. At equilibrium, your seesaw should be balanced. Once you apply the stress, you want to slant the seesaw to reflect the stress that has been added. From there, you can make conclusions. The conclusions that you can make are that equilibrium always shifts to the upside of the seesaw. The lower end of the seesaw has the species whose concentrations will go down, while the upper end of the seesaw has the species whose concentrations will go up. Let's look at an example. In this reaction for the synthesis of ammonia, we want to imagine the system at equilibrium. So we'll draw a balanced seesaw. And then we want to know what will happen to this system if we apply the stress of adding hydrogen. You can see that hydrogen is a reactant. So if I apply this stress, my seesaw will now shift in this direction because adding to this side will make it lower. And so what we want to ask ourselves is what's going to happen to the concentration of hydrogen? Well, since we added to this side, all of these things will go down while all of these items will go up. So that means that the hydrogen concentration will decrease, as will the nitrogen concentration. This is actually because by adding hydrogen, hydrogen will have more successful collisions with nitrogen, allowing it to turn into ammonia. So my reactant side of the seesaw is down, so their concentrations are down. My product side of the seesaw is up, so this ammonia will increase in concentration. So the question is, which side did equilibrium shift to? Well, recall that equilibrium always shifts to the higher end of the seesaw, because if there were little particles sitting on both sides of the seesaw, the particles will have to shift to the right in order to rebalance the seesaw. But very simply, you remember that whatever your seesaw does, equilibrium shifts to the upside. So in this case, equilibrium will shift to the right. Let's continue with this ammonia reaction. Let's predict what happens if we add the stress of adding nitrogen to the system. We can see that nitrogen is here. So that means that this side of the seesaw will become heavier. My seesaw will look like this. We know that the reactants are on this side and the products are here. All of this followed by, of course, our double-headed arrow. So since hydrogen is on the reactant side, the concentration of hydrogen will decrease, as will the concentration of nitrogen. This is because more nitrogen means more successful collisions with hydrogen. And the concentration of ammonia here on the product side will increase because it's on the higher end of my seesaw. Now, what direction does equilibrium shift? It always shifts towards the higher end of the seesaw. So in this case, equilibrium will shift to the right. That means that the forward reaction. Now let's see what will happen to the same system if we add the stress of adding the product, ammonia. So ammonia is on the product side. So if we make the product side of our seesaw heavier, our seesaw will slant in this direction. And so my reactants and then my products. So what you can see are that my reactants are up. So the concentration of hydrogen will increase, as will nitrogen, because they are both reactants. Now my product's concentration will go down. That's because adding more product will allow it to have more successful collisions, thus favoring the reverse reaction. And the final thing we need to determine is which way will equilibrium shift. But remember, equilibrium always shifts to the side that's up. In this case, equilibrium shifts to the left, or equilibrium shifts reverse. Let's continue looking at the system. Here, our stress is a little bit different because we are removing a substance, but it works the same way. Here, we're going to remove ammonia. If we remove ammonia, our product side of the seesaw becomes lighter. So our seesaw will look like this. Here are our reactants, here are our products. So that means the concentration of my reactants will go down. And the concentration of my product ammonia is up. Equilibrium always shifts to the side that is up. So in this case, equilibrium is going to shift to the right, or it's going to favor the forward reaction. Recall that heat can be written directly in the reaction. Endothermic reactions have heat as a reactant, while exothermic reactions have heat as a product. We can use this to determine shifts of equilibrium. As long as you write heat into a reaction, you are able to use the seesaw technique for stresses that include changes in temperature. So in this case, if I add heat or increase temperature of the system, it's the same as adding something to the product side, because the forward reaction is exothermic, heat is on the product side. So this is going to cause my seesaw to be heavier on the product side, or slant like this. So you can see my reactants are on the higher end, and my products are on the lower end. So the concentration of hydrogen, a reactant, is going to increase, as will nitrogen, while the concentration of ammonia on the product side will decrease. Equilibrium always shifts to the higher end. In this case, equilibrium is going to shift to the left. The left is the reverse reaction. Finally, let's look at pressure, which only affects gases. What we know is when we increase pressure, we shift away from the side of the reaction with more moles of gas. And when we decrease pressure, we shift away from the side of the reaction with less moles of gas. So let's look at this reaction. Notice that the coefficients indicate that there are 3 moles of gas on the reactant side, but only 2 moles of gas on the product side. So when we increase pressure, we want to alleviate that stress and go to the lower number of gas particles. So increasing pressure, we want to go away from the 3 moles and towards the 2 moles. We want to shift forward, or shifting right. So when pressure is applied to a gaseous system, the first thing you want to make sure is that you indeed have gases in your system. Now, all of these species are gases. So then the next thing you'll need to do is count the number of moles of gases on each side. On the product side, the coefficient of 2 indicates that there are 2 moles of ammonia gas. Now on the reactant side, I have 3 moles of hydrogen and 1 mole of nitrogen for a total of 4 moles of gaseous particles. Now when we increase pressure, we always want to favor the side that is opposite, the lower number. So if I want to favor the side that's 2, I want to draw a seesaw that is shifted to raise up the 2. Using this seesaw, I can see that the reactant side is down, so the reactants will decrease in concentration, while the product side is up, so it will increase in concentration. We want to shift to the side with 2 moles. That is on the right side. That is the forward reaction. Now we should carry out the same thought process for when we decrease pressure. So we count the number of moles of gas on the reactant and product side first. Here I have 4 moles of gas, and here I have 2 moles of gas. Now, since I'm going to decrease pressure, I want to go in the opposite to the higher number. So I'm going to raise up the 4. My seesaw looks like this, so I can raise the 4. What I know is my reactants are on the higher end, and so they will increase. And my product is on the lower end, so it will decrease. Now, when I look at this shift, I can see that I'm shifting to the upside, so my reaction will shift left. Left is the reverse. So the last condition we're asked about is the shift of equilibrium that occurs when a catalyst is added. Catalysts increase the rate of both the forward and the reverse reaction. Since they make both reactions happen faster, equilibrium is not affected by the addition of a catalyst. This is the end of your lesson on Lechatellier's principle, which examines how systems at equilibrium shift by increasing the rate of the forward or reverse reaction, causing changes in the concentrations to establish new equilibrium. Make sure you've taken good notes and you bring your questions to class. We'll practice a lot more together. See you soon.